The limit of a function, part 2. So in the last video, we looked at the limit of f of x as x approaches a, where we're looking at what on earth our function value is approaching as our input x is approaching a particular value. And we looked at a couple graphical examples where we were already given the graph of a function. Now we're going to take a look at limits of piecewise functions and limits of the greatest integer function without already being given a graph. When we're working with limits, it's important to note the difference between evaluating the function and evaluating the limit. Sometimes evaluating a function and evaluating a limit will give us the same value, but sometimes they won't. For example, if we look at f of 2 for this piecewise function, when our input is 2, our output is 3 at this closed circle. But if we look at the limit as x approaches 2 of f of x, well, we have to look at our left and right hand limits. From the right, I'm approaching 2, but from the left, my output is approaching 3. So my overall limit does not exist. For this reason, direct substitution alone cannot be used for potentially discontinuous functions. So that's where we have these gaps or holes in our function. Piecewise functions and greatest integer functions are frequently discontinuous. So that means that we have to be a little more careful as we evaluate these limits. Let's look at this piecewise function. This particular piecewise function has 3 parts. We need to take a look at each of these 3 parts. Which I will now color code. And we need to figure out what is going on as we switch between these 3 parts. So we need to look at the domain of each piece and look at the boundaries of each domain. So if we're looking at x is -1, well, we switch between the first piece to the second piece at x is equal to -1. That's where we switch. So we want to know what is going on with this first piece, this x plus 2, as x is approaching -1. So as our input is approaching -1, well, we can substitute that -1 into our function. So we have -1 plus 2, which gives us 1. So our function is doing something at that point, -1, 1. For this piece, we'll have an open circle, which I'm going to denote with that open circle symbol. Now let's take a look at what happens when we switch over to this next piece, so to this x squared. As we look at that -1, when we input -1 to x squared, that's -1 squared, which gives us 1. But this is a less than or equal to symbol this time, as opposed to just a less than. So we actually have a closed circle at this point, -1, 1. But that's not the only point that's on the boundary of the domain for this piece. We also have x being 1. So let's look at what this x squared is doing or approaching as x is approaching 1. So we have this 1, and when we input 1 into x squared, our output is also 1. But here we have just a less than symbol. So we have an open circle for this piece at the point 1, 1. And then last but not least, we have this piece here with our square root of x, and a domain of x is greater than or equal to 1. So when we input 1 to the function the square root of x, we output 1. And since this is a greater than or equal to symbol, we have a closed circle at this point. And now that we've figured out where the open and closed circles are for a function, we can sketch a quick graph. So I'm just going to put my -1, my +1 can be a little closer, my +1, my -1, and my +1. Then I'm going to plot my points. So I have a point at -1, 1. That's my open circle. And then I have a closed circle at -1, 1, so I kind of filled in that circle. Then I have an open circle at 1, 1. And then I have a closed circle at 1, 1. So I've actually filled in that circle. And then I can sketch each of these pieces. So I have my x plus 2. So I already know this point is here, and then my slope is 2. So my slope is 1. So I have another point going down. It's doing something like this. I know it's an increasing function. And then for this middle bit here, I have an x squared. So that would have a vertex at 0, 0. And then be a parabola between these 2 points. Hopefully a slightly more symmetrical parabola. And then starting at x is equal to 1, I have the square root of x. So I have my square root function, which is increasing, but at this kind of like weird shape here. Now that we have a graph of our piecewise function, we can use this graph to help us evaluate each of these limits. Even if you don't sketch a graph, you at the very least want to find the points where a function is switching, and whether or not you have this open circle or closed circle. I like to ask myself 2 questions as I'm evaluating limits for piecewise functions. The first question is, which piece should I be looking at? The second question is, are my left and right limits equal? In this case, I wrote it, are my right and left limits equal? Let's take a look. So we have the limit as x approaches -1 from the right. So if I'm approaching -1 from the right, that means that I want to be larger than -1, but still close to -1. So that means I'm looking at this piece of my function, where x is larger than -1, but still -1 is included on the domain of that piece. So as x is approaching -1 from the right, I'm approaching 1. Now we want to take a look as x approaches -1 from the left. So now I'm looking for inputs that are smaller than -1, but close to -1. So that's going to be this piece, because I'm getting close to -1 in that piece, but I'm also less than -1. And the limit as x approaches -1 from the left is 1. Since my left and right hand limits are equal, the limit as x approaches -1 for this piecewise function is 1. Now let's look at the limit as x approaches 1 from the right. So since we're approaching from the right, that means we're looking at numbers that are greater than 1. So our domain is greater than 1 at this bottom piece with the square root of x. And as we're approaching 1 from the right for that piece, for our x, our outputs are approaching 1. Next, we'll look at the limit as x approaches 1 from the left. So we need to be smaller than 1, but close to 1. And that is our middle piece here. The limit as x approaches 1 from the left, so where it looks like we'd have that x squared, would be 1. 1 squared is 1. So we're approaching 1. And since our left and right hand limits are equal, the overall limit as x approaches 1 of f of x is 1. Now we have the limit as x approaches 4. Well, we don't have to worry about our function switching over at x is equal to 4. That's just this piece of our function. When x is greater than or equal to 1, we're in that square root of x part of our function. So we just have to take the square root of 4, which is 2. Now we have the limit as x approaches negative 4. Well, we don't have to worry about switching over between our different functions at x is negative 4. So we just need to figure out which piece it is. So that's this piece. So we have x plus 2, so that's negative 4 plus 2, which is negative 2. And then last but not least, we have the limit as x approaches 0 of f of x. Well, the only piece that has that is our middle piece, where x is between negative 1 and 1. We're not switching between our different pieces at 0, and x squared is a continuous function, so we just have to look at 0 squared, which is 0. So we're really worried about which piece should we use, and if we're switching over between our different pieces, are the left and right hand limits equal? Let's look at another piecewise function. So we want to start by finding the points at the edges of the domain of each of our pieces. So we have the function x squared when our domain is x is less than negative 1. So we need to substitute this negative 1 into our x squared function, and we get that our output is 1. But since this is strictly a less than function, we have an open circle. Next, we'll take a look at this 1 over the absolute value of x, which has a domain of negative 1 is less than or equal to x is less than or equal to 2. So we have 2 boundaries for this particular domain, so we'll need to check each of them. So when we input negative 1 to this function, we get 1 over the absolute value of negative 1, which is 1. Since we have this less than or equal to symbol, this point is included. Then we'll check the other boundary of our domain, which is 2, and 1 over the absolute value of 2 is 1/2. And this is an open circle. Then the last piece of our function is x plus 3 when x is greater than or equal to 2. So we'll switch that boundary of our domain, which is 2, and then x plus 3, so 2 plus 3, is 5. And since we have this greater than or equal to symbol, that means that we have a closed circle at the point 2, 5. And now we want to take a look at the limit as x approaches negative 1 of f of x. Well, as x approaches negative 1 of f of x, we're switching between the x squared part of our function and the negative 1, and the 1 over the absolute value of x part of our function. So this means that since we're switching, we'll need to check the left and right hand limits. So let's start with the limit as x approaches negative 1 from the right of f of x. So this means that we're starting with values that are larger. Well, the limit as x approaches negative 1 from the right, that's going to be this middle piece. And as x approaches negative 1 from the right of f of x, we get 1. We also want to take a look at the limit as x approaches negative 1 from the left of f of x. So we're looking at where our function inputs are less than negative 1. So that's going to be this top piece here. And as x approaches -1 from the left, so as x approaches -1 for this top function, our output approaches 1. And since our left and right hand limits are equal, our overall limit as x approaches -1 of f of x will be equal to 1. Now, instead of looking at the limit as x approaches -1, we'll look at the limit as x approaches 2. This is again an x value where we're switching between two different pieces of our function. So we're switching between our 1 over the absolute value of x and our x plus 3. So that means we'll need to take a look at our left and right hand limits. So we have the limit as x approaches 2 from the right of f of x. So we're looking at the piece where our x values are greater than 2. So that's going to be this x plus 3 part of our function. So the limit as x approaches 2 from the right is going to be 5. And then we need to look at our left-hand limit. So that's the limit as x approaches 2 from the left of f of x. And that's going to be looking at what happens in the piece that is where we're smaller than 2. So that's our 1 over the absolute value of x piece. So our left-hand limit is going to be 1/2. Now, our left and right-hand limits are not equal. So that means that the overall limit, so the limit as x approaches 2 of f of x, does not exist. The last function that we'll look at in this section is the greatest integer function. The greatest integer function outputs the integer that is less than or equal to x. So in some ways it's kind of a confusing name because we're actually looking at what is less than or equal to x. You can think of this as rounding down to the nearest integer. So if we want to graph this function, well, 0 is the greatest integer that is less than or equal to 0. And 1 is the greatest integer less than or equal to 1. And that continues for each of our integers. The tricky part of this graph is what happens in between the integers. So if we're looking for something like 0.5, 0.5 is right in between 1 and 0. This 0.5 is our x. Well, we're going to return the number that is less than or equal to this x. So we're rounding down to the nearest integer, which is 0. So that means that if we're in between 0 and 1, our output is going to be 0. But then as soon as we hit 1, our output is 1. Similarly, if we're looking at an input of 1.5, that's in between 2 and 1. But for the greatest integer function, we're interested in the integer that is less than or equal to our x. So if we input 1.5, we'll actually output 1. So anything that is in between 1 and 2 will output 1. Then as soon as we reach 2, we start outputting 2. And this is how it's going to continue along our graph. And the graph makes it much, much easier to actually evaluate each of these limits. So let's put the graph to good use to evaluate the limits. we want to find the limit as x approaches 3 of f of x. So we're looking as we approach 3 from the left and right, what's happening to our function? Well, from the right, as I'm approaching 3, from my input, my output is also approaching 3. And from the left, as my input approaches 3, my output is approaching 2. So my left and right limits are not equal, so the overall limit does not exist. Now let's take a look at the limit as x approaches 3.2. So that's somewhere in between 3 and 4. The limit from the right is approaching 3. And if I look at my left-hand limit, I'm also approaching 3. Since my left and right-hand limits are equal, my overall limit as x approaches 3.2 is 3. Next up, I have the limit as x approaches 1 from the right. So now I'm only looking at my right-hand limit. So starting from the right of 1, and as my inputs get closer and closer to 1, my outputs are also approaching 1 when I'm looking at that right-hand limit. If I were to look at the left-hand limit, I'd see that my left-hand limit is 0. So my overall limit doesn't exist, but each of my left and right-hand limits still exist. Now we'll look at the limit as x approaches 2 from the left. So as I'm approaching 2 from the left, my outputs are approaching 1. There we go, I can actually write 1 now. And then this was an error, and it will not let me fix it in the soft copy of the notes. So this was supposed to just be a positive 2.4. There shouldn't have been a minus sign, and I apologize for that. So we have the limit as x is approaching a positive 2.4. So from the right, as we approach 2.4, our output seems to be approaching 2, and as we approach x is equal to 2.4 from the left, our output is also approaching 2. Now we have the limit as x approaches 0.2. So as we look from the right, it seems that our limit is approaching 0. And as we look from the left, we find that our limit also approaches 0. Just 2 more limits. We have the limit as x is approaching negative 4. So from the right, approaching negative 4 from the right, we get this negative 4. But if we were to continue this graph, it would look something like this. We'd have another step that we'd switch to at negative 4. So our overall limit does not exist. And then last but not least, we want to find the limit as x approaches negative 2.3. So negative 2.3 is somewhere in between negative 2 and negative 3. If we look at our right-hand limit, as x is getting closer and closer to negative 2.3, our y's are getting closer to negative 2. And as we approach from the left, and x gets closer to negative 2.3, y, or whatever our output is, f of x, is getting closer and closer to negative 3 as well. In the next section, we're going to look at an algebraic approach to evaluating limits, as well as something called the squeeze theorem. And this is opposed to this section where we looked at a graphical approach to evaluating limits. Since we're looking at an algebraic approach, that means that all of your algebra skills are going to be necessary in order to be successful with this section. So if you find the next section rather confusing, you might want to go back and review some of your algebra skills.